This is the first lecture where we go into a bit of detail about linear models. Now, I've already actually talked about linear models quite well, at least in one lecture. I was mentioning it a bit. But this is the first lecture where we start to look at it in detail. So hopefully, some of the things we cover will seem familiar from the first week of term. And we'll just sort of push it forward a bit. So what we're going to cover today, I'm going to talk about what the linear model is. Describe how we assess the fit of models, and I'm also going to talk about some issues around how we estimate parameter. I've talked about this before, estimating parameters, so we get these beta values, and I'm going to talk a bit about some things we can do to make sure that those betas and significance tests around those betas are accurate. And in your practical class, you're going to start putting this all into practice using SPSS. And they'll talk a bit more about interpreting what comes out of SPSS as well. Okay, so we've seen before what a linear model is. And it looks like I bought a pointer today. It's all green and nice. We've talked a bit about what linear models are. So I've chucked up this equation before. And a sort of a nicer way to put this equation is to replace some of the symbols with some words that actually make sense. So we're trying to predict an outcome, which we normally denote by y, from some kind of model. So before, when I put that up, I just would have put the word model to try and keep things really simple. But we've seen that, for example, the word model can be replaced with this thing. And this is a linear model, or the equation of a straight line. And whenever we make predictions from a model, there'll always be some kind of error attached to that prediction. So it will never be perfect. So what we're talking about today really is the bit more of the pragmatics of fitting this kind of linear model, and also looking at how this model extends to more sort of slightly more complicated scenarios. So when we looked at this before, the equation of a straight line, we had a bit of a chat about these kind of beta values and what they represent. Something's gone a bit weird with my screen. Half my slide's missing. Does it do that?
Yeah, it's got a bottom. It's really
Okay, so it's not a personal thing. It's not a vendetta that the machine has against me. Okay, well we'll muddle through as best we can. I'll just have to point at things that don't exist, and that'll be amusing. So the beta 1 in that equation is, well, actually both the betas are known as parameters. And that's just a kind of a confusing name for, actually I don't really know what for, it's a confusing name for a parameter. A parameter is just a b, right? So these b's represent certain things. So we've seen in week 1, we had a talk about this before, and the beta 1, so a beta associated with a predictor variable, represents the strength or direction of the relationship between that predictor variable and the thing that you're trying to predict. So that beta tells us something useful about the relationship between the predictor variable, that's the x in the equation, and the outcome variable. There's also a beta 0 in there, and that tells us something about the value of the outcome variable if all our predictors were 0. So in the simple scenario where we've only got one predictor, this is often referred to as the intercept, and you'll have seen it graphically as, you know, the point where, if you've got a regression line, the point where the line crosses the y-axis. But I want you to think about it more in terms of it's the value of the outcome that you would get if all the predictors were 0. So in a way, you can think of, in the simple case where you've only got one predictor, you can kind of think about both of these things as defining the shape of the model. And as you'll see, as we extend the model to have more predictors, that still applies. The betas really tell us what the shape of the model is. So they really define it's kind of what it looks like, basically. So I kind of equate this a bit to, if you've ever been to West Street, which I haven't been to at night for a very long time indeed. But West Street's like where all the nightclubs in Brighton are. And if you go there at certain times of day, during the week, there's often lots of drunk people staggering around. And when you're drunk, you kind of come out of the nightclub, you don't really know where you are or what you're doing. And that's a bit like a regression line. Left to its own devices, a regression model or a linear model will just float around in mathematical space without a care in the world, going, I don't know where I am or what I'm doing. Now, what the beta 0 does is that's like a kind of it's a kindly policeman, if you like. He doesn't arrest the regression line, but instead he tells it where it is. It says you're in West Street. It may even nail his feet to the floor or something. So it positions it in geometric or mathematical space. It gives it a place to stand, if you like. So rather than go, I'm the regression line, it goes, right, there you are. You are fixed there. And what the beta 1 tells us is it tells us, in a way, how drunk the regression line is because it tells us the shape. So is it leaning this way or is it leaning that way? Is it, well, it actually would never be sort of completely vertical. Or is it like completely like horizontal? Oh, whenever I do this, I hurt myself. Is it completely, ow! Is it completely horizontal? Now, if a regression line's horizontal, I was right, I hurt myself again. If it's completely horizontal, what does that mean? It means there's no relationship at all. If a regression line is flat, if the beta is 0, that means no effect whatsoever. So it's like, you know, it's got so drunk it's just dead. No effect at all. So the betas tell us something about the shape of the model. So we can start using some slightly frivolous but real examples of what we might predict and from what. So we could predict geekiness, for example, from how much you like statistics. So if you had some kind of psychological index of geekiness, that may well be predicted by your love of statistics because, you know, people think that people who like stats also like other things like sci-fi. It's not true at all. So that's an example of a simple model, and we're going to see how we can extend it. Now, the important thing is we've got this beta 0. It tells us how geeky our sample would be if their love of statistics was 0. And we've got this beta 1 which tells us about the relationship between these two variables. So if this beta 1 is positive, it means that loving statistics makes you, well, doesn't necessarily make you, but is related to being more geeky. If it's negative, it means that loving statistics is related to being less geeky. And if it was 0, it would mean no relationship at all between loving statistics and being geeky. So, just to ram this home, betas tell us about the shape of the model. So they define the model for us. They tell us what it looks like. So, for example, we could look at 3 models that have the same... Oh, dear, oh, dear, oh, dear. That have the same intercept, so they have the same value of the outcome as each other when the predictor is 0. But they have different shapes. So the beta ones are different. Now, this is an example of your verbal coherence as a function of how much you drink. So, if you're a really hardened drinker, you'd have a beta of 0. So the more you drink, so quantity of alcohol is going up along this axis. So the more you drink, it has no effect whatsoever on your verbal coherence. You start off as verbally coherent as you are, which is sort of midpoint of the scale, and that just doesn't change. You drink and drink and drink and drink and drink, nothing happens. That would be slightly unusual. What normally happens, so for most people in the population, we get a negative relationship, so this would be a negative beta. The more you drink, the less coherent you become. So at a certain point, you're probably just incomprehensible to everyone. It's not inconceivable that you could have a positive relationship. Perhaps if you were a bit socially anxious or whatever, so you're normally quite shy, so maybe you're not particularly verbally coherent when you're sober because you get very anxious and worked up. But a bit of alcohol suddenly kind of loosens the cogs, if you like, and you become slightly more verbally coherent because you've stopped worrying about what you're saying and things like that. So this just shows you how the betas define the shape of the models that we fit in a very simple scenario. The opposite situation would be if we have a look at models that have the same shape. So they all slope down. So this is, as I said, the sort of typical scenario. The more you drink, the less coherent you become. So the models are all sloping down, but they have different intercepts. So the samples have different natural levels of verbal coherence at sort of 0, basically, so when they're sober. So this would be a sample of people who are very, very coherent, and these people are less coherent to begin with. But I just want to make the point that these betas, whatever the model looks like, however complicated it gets, they just tell us about the shape of the model that we're fitting. So they define what it looks like. So let's look at an example. This is the example that's going to be used in your handout. It's the example from the book. And this is an example of predicting record sales, or I think in a fit of trying to keep with the times, I may have updated this to album sales, because people don't buy records. Well, actually, some of them do. I still buy records, but I'm old. So anyway, album sales, or whatever you want to call them, I don't know, downloads, whatever the kids are into these days. So this is like thousands of record sales, and we're trying to predict it from advertising budget, because how do record companies or any company try to sell things? They spend money on advertising. So a very simple model might be to just fit a basic one predictor kind of model. So can we predict record sales from the amount of advertising that we spend? The answer to that is kind of yes. So we've got a nice kind of linear trend there. And it's pointing upwards. So more you spend, more records you sell. What happens if we want to expand this model? So if we're not just content to look at advertising, but if we suddenly decide, well, advertising is all very well, but we can probably do a better job of predicting record sales if we measure some other things that might be important. So, for example, we might measure airplay on radio, because that's very important. People listen to the radio, they hear songs. Before they know it, they like the songs, and then they want to go and buy the album. This is, it's kind of like the mere exposure effect, really, in real life. So you get this a lot. Before records come out, you'll hear them on the radio lots and lots and lots of times, until even there are records. Well, so for example, when I was a lad, I used to hate a lot of. I was sort of growing up in the 80s. Well, a bit of the 70s, but mainly the 80s. And so I used to, as you might imagine, like the Iron Maiden and all stuff like that. But that wasn't particularly popular, and all the stuff in the charts was kind of things like Wham, and Wham's the only one I can think of now, actually. But anyway, so there's a lot of Wham in the charts, and I hated it with an absolute passion, because like when you're a teenager, you kind of have a bile for these sort of things that. It's quite phenomenal. So, I'd be listening to my Motorhead albums or whatever, and if I heard Wham, or, heaven forbid, I actually went to like a school disco or something. We used to have them back then. Or at least they were called discos. They probably have like school nightclubs now. And there was some Wham on. I'd just be like, oh, Wham! I hate Wham. But over like the last 20 years, where you keep hearing this stuff over and over again, now when I hear Wham, I mean, I don't want to go out and buy it, but I sort of think, yeah, it's not so bad. Don't know what I used to get so riled up about. So you get this mere exposure effect. So the amount you play stuff on radio, or the amount you hear stuff, you tend to, not always the case, but you tend to end up liking it more. My parents, for example, became pseudo Iron Maiden fans as a result of listening to what was coming out of my bedroom for 5 years. Anyway. So if you want to add another predictor, how does our model change? So it's very easy to conceptualize one predictor. We have a line. It's all nice and everything. If we add predictors, we get something called a regression plane. That's not the crappiest joke you'll hear on this course, but it's one of them. So you get a regression plane. Now, what does a regression plane look like? Half of it looks like this. So rather than having a sort of a nice graph with two axes, you end up having an axis in sort of a third dimension, and your line changes from being a line to being a plane. So this is a nice little video. It's not the most entertaining video, it has to be said, but it's just to kind of illustrate the shape of the plane that we would have fitting this model. So one of our axes is now representing plays on radio, one of our axes is advertising budget, the yellow dots are the data that we've collected, and the green thing is the regression model. So it's a line that's turned into a sort of three-dimensional plane. But the basic principles that applied with a line still apply with this plane. So the betas that we have, as we'll see in a minute, still define its shape. The intercept still locates it in sort of mathematical space, for want of a better phrase. Everything still applies. It's just we're making things more complicated, and the model starts to look more complicated, but essentially all the principles are the same whether we have one predictor or many predictors. So what does this look like as an equation? If you add predictors to a linear model, people typically refer to this as multiple regression, the multiple referring to the fact you have multiple predictors, not the fact that you're doing lots of regressions. each predictor will have a parameter associated with it. So that's a beta value that's kind of latched onto that specific predictor. So when we have one predictor, our model, hopefully you might have a handout, model looks like this thing that would be down here if it was projected. So you've got the beta 0, you've got one predictor, an x, and a beta associated with it. If we add another predictor in, or more predictors in, we just add them in. So we add a new x, and we could give that a better name than x. We could call it airplay or something like that. And again, we give it a beta, which tells us something about its relationship to the thing that we're trying to predict. And all the equation at the bottom, for those of you that can see it on your handouts, tells us is the ... just means that we can carry on adding things in until we've run out of predictors that we want to include. So the linear model, one of the beautiful things about it is in a way, there's a very simple idea, is that you put a variable in, and although in these equations we tend to denote them by x's, which is not the nicest way to denote them, but you can think of those x's as just the name of the variable. We can just plonk them in, and whenever we plonk one in, we have to give it a beta. We give it a parameter that estimates what the relationship between that predictor and the outcome is in the population. So betas attached, I know I've said this like a million times, but you can never reiterate this too much. So the betas attached to variables tell us something useful about the relationship between a particular predictor and the thing that we're trying to predict. So a few examples of multiple regression, or regression with several predictors. We could look at how bored people are. This plays on my mind a lot. Based on how much time they'd spent in a lecture, for example. So this could be a variable ranging from 0 to 50 minutes. Presumably, your boredom goes up the more you're listening to me drone on. But we might also add a different predictor. So this is a different x, but I've given it a more useful name of the topic that I'm talking about. Perhaps you'd be less bored if I was talking about what I did at the weekend rather than talking about linear models. It's questionable whether that's true, but it could be the case. Now, the interesting thing is that would be a categorical variable. Am I talking about stats versus am I talking about the jolly activities I got up to at the weekend? And you might think, well, surely you can't put that in the linear model. Actually, you can. In a couple of weeks' time, we're going to look at that in more detail. But I just want to flag it here that you can have categorical predictors. You just have to include them in a very specific sort of way. Another example, hangovers. How bad is your hangover? Well, obviously, that should be a function of how much alcohol you've had to drink the night before. More you drink, worse your hangover should be. But we might also factor in another variable such as how much sleep you've had. I don't know. Arguably, the less sleep you've had, the worse your hangover will be. I don't know. That's possibly not always the case. I don't know. And we could even extend this further to add another predictor. So perhaps, personally, I don't smoke. But I know some people that do, and some of them have said to me that they think, if they've really had a lot to smoke, as well as a lot to drink, their hangovers are worse. So maybe we might want to factor that in as well. So we could change our model to just include another predictor variable of how many cigarettes they'd smoked or whatever else they might smoke. And you can see the model's just extending each time. We're just literally putting in a new predictor variable. Rather than using x's, I'm just giving them a bit more helpful names, like the name of the variable. But the point is each one has a beta, and this beta is going to tell us about the relationship between a particular predictor and the outcome. So in a way, it's a very simple idea. You've got, as I said, one equation, the only equation you ever really need, which is this equation of a straight line. And we just sort of tweak it a bit. We just add in new predictors, and each time we do, we give it a parameter that we try to estimate. So the idea behind the linear model is really quite straightforward. Now, when we have multiple predictors, as I said, we get a regression plane. So this is going back to our... it's going back to Doctor Who. It's going back to our example of record sales based on advertising budget and number of times the record was played on radio. And all I want to point out is that the betas, as well as telling us about the relationship between a predictor and an outcome variable, they also do define the shape of this. You won't be able to see that. Define the shape of this plane. So the beta 0 will be the little peak where the plane sort of hits the y-axis, or it's the value of the outcome when both predictors are 0. The beta associated with radio play will represent the slope of this side of the regression plane. So this would be the beta associated with radio play. And the beta associated with advertising budget would represent the slope of that side of the regression plane. So basically those betas tell us where the regression plane is located and also what shape it is. So you imagine this, I know it's a crap prop, I'll admit it. But imagine this is your regression plane, so it could be completely flat, which would be no relationship at all between either predictor and the outcome, or it could be slopes like that, it could be slopes like that, it could be slopes like that. So it's like it's flying around geometric space. The beta 0 will lock it in to a certain place. It'll say, right, you are there, and then the beta 1s and beta 2s tell us about, how it's, whether it's at that angle or that angle or that angle or whatever. So the betas literally define geometrically what the model looks like, but in more practical terms, they tell us about the strength and direction of relationship between predictors and outcomes. So nothing really changes. Now, if you add a third predictor, this is where the TARDIS comes in, it gets more complicated to visualize the model because you'd have to go into like the fourth dimension, and if you had like 5 or 6 predictors, you'd be going to 5th and 6th dimensions, and everything gets very confusing. And I'm not really sure how you'd visualize that. Maybe like a regression plane that transcends time and space or something. I don't know. But anyway, the basic principles apply. You can just keep adding in predictors, and the betas will tell you about the relationship between those predictors and the outcome. But also, if you could visualize, in 5 or 6 dimensions, what the regression model looks like, those betas would also be defining its shape. So, the betas are pretty important, so I'm going to talk a bit about them. Now, we've talked about parameters before in the first week, I believe. In the context of the linear model, these betas are, as I said, they're estimates. They're known as parameter estimates. So the parameters are the actual values in the population. They're the things that we would like to get hold of, but we can't. So instead, we fit a sample, we fit a model to the sample data that we've collected, and using that sample, we estimate the parameters. So they're called parameter estimates because we can't get the actual values in the population, so we're estimating them based on our sample. Now, we also came across the idea in week 1 that any parameter at all, whether it's a mean or whether it's a regression coefficient like we're talking about here, you can construct a confidence interval around it. And that confidence interval will give you the boundaries within which the population value is likely to fall. Now, remember that these betas represent the relationship between a predictor and an outcome. And also remember that if a beta is 0, if the line is dead flat, that means there's no effect at all. So if a confidence interval contains 0, so if 0 falls within the boundaries of it, what that means is it's possible that the actual effect in the population, the value of the parameter in the population, could be 0. In other words, no relationship at all. So if you see confidence intervals that contain 0, that means that basically the predictor could have no relationship whatsoever with the outcome. So in other words, it's not a very good predictor. You can also more formally test predictors using a significance test, and actually it uses a t-test. And what that test does is to compare the value of the beta that you've estimated against 0. Because if you think about 0 as a sort of null hypothesis, like I said, 0 is a flat line, no effect whatsoever. So a significance test of whether beta is 0 is going to tell us whether or not the predictor is significant. So if you get a sort of a p-value less than 0.05, it means that predictor is significant. But bear in mind what I said before about significance and large samples and things like that. It's not always that useful. What is definitely useful is the fact that the beta also, in its own right, is an effect size. And I talked about effect sizes in week 1, and I said they're useful because they're not so biased by the size of the sample that you have. So you can interpret them independent of significance and things like that. So it may be, for example, that you fit a linear model in quite a small sample. You get a big substantial value of beta that looks like there's a sort of an impressive relationship between the predictor and outcome. But when you look at the significance, it's not significant just because you've got a small sample. So all of these things are things, when interpreting betas, they're things to consider. What does the confidence interval look like? what's the significance test, and what is its value in its own right, irrespective of everything else. We also saw in week 1 that parameters can be biased by various things. So we talked a bit about, or very broadly in the second lecture, about how we estimate parameters. And I gave a very crude description of what's known as the method of least squares. Now, in regression, we still use the method of least squares, but you'll sometimes see it referred to as OLS, which stands for ordinary least squares. But it's the same principle that I was talking about in week 2. So the idea that we estimate parameters that give us the least amount of squared error. We also saw in maybe the third lecture, I think, when we were talking about bias, that if we do significance tests or if we construct confidence intervals around parameters, they depend upon certain things being true. One of them is that the sampling distribution of that beta should be normal. We should have homoscedasticity or homogeneity variance, whatever you want to call it. And our observations should be independent from each other, so we shouldn't have related observations. If those 3 things are true, then we can trust the significance tests and confidence intervals that are generated. We also saw that our parameter estimates, so the estimates of beta, are optimal using ordinary least squares when the errors in the model are normal, and again, if we have homoscedasticity. So I'm going to talk about this a bit more next week. What I want to focus on now is this idea of how to ensure accuracy of the significance tests and confidence intervals. And we can use this thing called bootstrapping. So next week we're going to look at how we identify non-normal or non-normality and heteroscedasticity. And we've already talked about it a bit in lecture 3. If those assumptions are violated, so if we think, we can't trust the significance test, we can't trust the confidence intervals, we can do something known as bootstrapping, which I am now going to attempt to explain. The idea behind the bootstrap, we've got this sample of scores, of 30 scores that we've got, and what we're trying to do is to use this sample to create what are known as robust estimates of the confidence interval and the actual parameter itself. So the bootstrap is a process through which we can generate robust, or so-called robust estimates. Now the bootstrap works on the principle of using the sample data to generate robust estimates. I'm really regretting turning that off, by the way. So how does it do it? Right. Well, I need my pink hippo, because whenever I'm explaining anything complicated, the pink hippo needs to come out. And he's living in a box today. So imagine we have our 25 scores in here. They're actually ping pong balls, but each ping pong ball has a number on, and that number relates to one of the numbers that was on the frequency distribution that was up there a minute ago. So we've got 25 scores, all represented on a ball. So this box basically contains our sample of scores. Now, let's say we wanted to estimate the mean of these scores, or let's say we wanted to do a bootstrap mean, so it's just a bit simpler to explain. So the parameter we're interested in is the mean. So what do? Well, first of all, we need to construct what are known as bootstrap samples. So this is something that SPSS does, and you don't really need to worry about it doing it because it does it very quickly. But what it's doing is creating these bootstrap samples. So what's a bootstrap sample? Well, imagine you've got your sample data, and imagine your SPSS. You pick a value out, just one. So it's a value of 3. So this is your first value, and then you give it to the magic pink hippo that lives inside SPSS, and he memorizes that value. So he memorized that value of 3. And it looks like he has a small brain, but in fact it's enormous. So he memorizes it, and then he spits it back into the sample. And then he takes another one. It's a 1. He memorizes it again. It's quite important that he eats it to memorize it, or sucks on it for a bit, like a gobstopper. And so he memorizes it again. So he's got a 3 in his brain. He's now got a 1 in his brain, and then spews it back in. So this is known as resampling, because we're taking a sample score and then we're putting it back. Shall I pick on someone else? Then we take another number. So this time it's a 0. Again, hippo memorizes a 0. So he's got a 3, he's got a 1, he's got a 0 in his brain, he's going, thinking about it, memorizing it, spews it back in. Then he takes another one. I need to do this for a while this kind of warms up. So he's got a 2 now. Nom, 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 nom. Memorizing the 2, memorizing the 2. And then he spews it back in. So he does this lots and lots of times. So he's randomly sampling a number, he's memorizing that number, and then he's putting it back. So he could pick the same ball twice, and that's fine. It doesn't matter. So he's putting it back each time. And that's known as a bootstrap sample. So that sample could be, it could be 5 scores, or it could be as big as the sample itself, because each time we're putting back the score. So what he does then is he's got a bootstrap sample. It's all in his head, and then he goes, and he works out the parameter within that sample. So we go, okay, you've got a bootstrap sample. What's the mean of those scores? He goes, 2.4, apparently. So we then have what's known as it's a parameter from the bootstrap sample. So we've got one parameter, one bootstrap sample. And then, because he really likes doing this, he does it again. So we go, picks the ball, memorizes it, it's a 2, picks another ball. It's like hungry hippos, quite literally. He memorizes a number, takes another one, another one. Oh, he says that one doesn't taste very nice. So he does that again. That's another bootstrap sample. He's taken, say, 10 numbers out, he's memorized them all, and then works out the parameter. It's 1.6. So in his previous bootstrap sample, he got a mean of 2.4. This time he's got a mean of 1.6. Oh my God, he's going to do it again. In he goes. 2.2. 3 bootstrap samples now. Each time, he's randomly taken numbers out of the sample. He's worked out what the parameter he's interested in, the mean, and he's kind of made a note of it somewhere on a little notepad somewhere. On the screen, in fact. Guess what? He's going to do it again. This is very tiring. It's getting more frantic, but he's done it all. Same process. His brain's exploding now. He's now got 4 bootstrap samples. He's calculated the parameter in each one. Now it's 4.2. So you can see the parameter estimates are different in each sample. And that's fine, because we're not interested in them individually. What we're interested in is doing this lots and lots and lots of times. Now you'll be glad to know I'm not going to demonstrate this for the 2,000 times that SPSS will do it. But it's this basic principle of creating bootstrap samples, working out the parameter, and then SPSS will do that 1,000 times. So it will end up with 1,000 bootstrap samples. The hippo of bootstrapping will be very tired. By the 1,000th sample, he'll be like, oh, I want to die. But what we'll have is 1,000 bootstrap samples and 1,000 estimates of the parameter. Now, I decided to not have 1,000 numbers on the screen. In fact, Sussex decided to not let me have more than 10 on the screen. But anyway, so the principle is we've got lots and lots and lots of these numbers. There's another 3 rows of these numbers below. Now, what's interesting about that is we could then take, say we want to know what the bootstrap or robust mean of these samples are. Well, we've got, say, 1,000 means, 1,000 estimates based on 1,000 bootstrap samples. We can just simply average those estimates. And that will give us a kind of a bootstrapped average, if you like. So that's one thing we can do. We can use bootstrapping to actually estimate the parameter in a way that's unaffected by the distribution of scores. By taking samples from our sample, these bootstrap samples, and working out the parameter within each sample, and then averaging across them. What happens more often than doing that is we rearrange them in order of, well, again, SPSS does this behind the scenes. You can rearrange them in order of size. So these are just going to disappear and then hopefully materialize in order of their size. Again, this would be better if you could see the whole screen, but essentially there's 40 scores here, and then now they're the same scores as before. It's just I've ordered them from smallest. That was the smallest Bootstrap parameter that we got, through to the largest Bootstrap parameter, which on my screen is 7.6. Now, having arranged them in order, we can literally compute a confidence interval based on the limits between which 95% of those values fall. So in this sample of 40 Bootstrap samples, that would actually involve just cutting off the top and bottom score. So this is the point at which the sort of middle 95% of scores lie. So when SPSS is creating a Bootstrap estimate of the confidence interval, this is sort of what this is known as a percentile Bootstrap. This is what it's doing. It's taking like 1,000 Bootstrap samples, it's working out the parameter in each Bootstrap sample, then it orders them, and then it works out the limits between which 95% of them fall. So rather than, normally when you work out a confidence interval, you do it sort of using equations, and this is sort of a way of doing it empirically. You sample from your sample, and you work out the parameter in each of your Bootstrap samples, and then you work out the limits within which 95% of them fall. I've just realised I haven't needed a hippo on my hand for about the last 3 minutes, but it's reassuring, it's comforting. So this is what bootstrapping is. It's taking these Bootstrap samples, it's working out the parameter you're interested in within each sample, and then you can construct a confidence interval based on the limits within which 95% of those scores fall. Now, from a practical point of view, you don't need to worry about all that going on. I just wanted to explain what's happening in the computer. As far as you're concerned, you will just get, if you opt for bootstrapping on SPSS, you'll get two output tables rather than one. So you get a normal output like this. This won't necessarily make any sense to you until you've done your practical class. But essentially, we've got predictors, we've got betas, so estimates of what the betas are, and then estimates of their significance, and also the confidence interval for each beta. So, for example, the population value of this, essentially, so the relationship between number of plays on radio and how many record sales you've got. The sort of point estimate in our sample is 3.37. The confidence interval is 2.82 and 3.92. So basically, the population value is likely to fall between those two values. Now, what you get is a table underneath which has Bootstrap versions of those significance and confidence intervals. So all it really means is if your assumptions are broken, just ignore these confidence intervals and these significance values and look at the ones down here instead. So from a practical point of view, if all the resampling stuff didn't make any sense to you at all, basically you just look at this table and ignore this table, essentially. So that's a good practical way, if you've broken assumptions, of just knowing that your confidence intervals and significance tests will be what's known as robust. It means they're unaffected by the fact that your distribution is not normal or you've got heteroscedasticity. So having estimated these betas, and we've fitted a model, we kind of know what it looks like, we have to then try to assess how it fits. And there's sort of two ways of doing this which are commonly used. So to change the example a bit, I'm going to have a look at whether using Facebook turns you into a monkey. Because there's evidence that it does. This is a bit anecdotal. I know this is a good friend of mine who he got really obsessed with Facebook a couple of years ago. Like, she couldn't do anything until she'd been on Facebook for a few hours. She'd get up in the morning, go on Facebook before going to work. Then at work, she was on Facebook a lot of the time, and then eventually she got the sack because she was on Facebook so much. And eventually she ended up living in a gutter. It's a very sad story. But also, she turned into a monkey. So I thought, I'd test out whether the amount of time you spend on Facebook actually can turn you into a monkey. So I did a bit of a study. I measured people's monkeyness. I mean, before Facebook was invented, my arms were completely unhairy, but look at the state of them now. It's only going to get worse with Twitter. So we've got monkeyness evaluated on a 7-point scale, and down here would be ours on Facebook. So there's a few things we can assess. These are the data that we've collected. Now remember that if there's no effect whatsoever, if there's no relationship between these two things, you'd get a flat line. So we can represent this by the mean of all the scores that we've collected. Completely flat line. It predicts, no matter how much time we spend on Facebook, it predicts the same level of monkeyness, which is 4 on the scale. Now, if you remember back to the first week, we had a look at how we can compute error or look at fit. And we said we could use deviations. So we could use the difference between what our model predicts, so that's the line, and what the actual scores we observed. So this is when we were looking at things like variance and standard deviation. So we had these deviations, or also known as residuals or errors. They're all the same thing. And if you remember, what we said was we can't just add these up because some of them will be above the line and some of them will be below the line, so they'll kind of cancel each other out. So if we want a total, it's no good to just simply add these deviations because some will be negative, some will be positive. So what we do is we square them and then we add up the squared values. So this is what we're doing here. We can work out a sum of squared error for a sort of a baseline model, a model where there's no effect at all, and that is the overall mean of monkeyness. And this will give us an idea of how much variability there naturally is in monkeyness if we don't include our predictor as a predictor. So this is just telling us how much variability in scores, monkeyness scores, we have in the first place. So if there's no effect, if we fitted like a flat model, if you like, how much variability in scores do we get? We can then fit our model. So the model we fit will look like this. So it's a straight line. And again, we can look at these deviations. So our model will, for this score, it predicts the point of where the line is. So it'll predict a value of about 5. But actually their monkeyness score is a bit higher. Here we would predict a score of 3 and a bit, but actually their monkeyness score was a lot lower. So we've got these little errors in prediction. So we can work out the error in the model in exactly the same way. So it's just using this idea of sums of squares. So we work out the deviations, the difference between what's predicted by the model and what we actually observe, and we square them, and then we add them all up. Now, hopefully, if our model is good, the error that we get when we fit the model will be a lot smaller than the error we get when we just use the mean of scores, when we use a line representing no effect at all. And that's known as the model sum of squares, and it's the difference between the two lines. So you need to kind of sort of ignore the data points a bit here. So it's saying for this data point, what's the difference between what the mean predicts and what the line predicts? For this data point here, what's the difference between what the mean predicts and what the line predicts? And this is it's the difference between the other two sums of squares that we talked about. But this represents improvement, essentially. It's saying, if we use the mean, this is the prediction we get. If we use the line, this is the prediction we get. What's the difference between the two? Now, if we have several predictors, the same principle applies. It's just rather than our baseline being a flat line, our baseline becomes a flat plane. So this is all this slide is there to show you, really. That the principle that I've just talked about, it applies if you've got lots of predictors or if you've just got one. It's easier to explain if we look at one predictor. But if we had another one, we'd get exactly the same scenario. It's just our baseline model would be a flat plane rather than a flat line. So to test the fit of the model, we can use sums of squares. And I told you earlier on in the module that sums of squares are important. We can use total sums of squares, which tell us the total variability in score. So you can imagine if you'd like baked a cake, this will be how big your cake is to begin with. We can look at the error in the model. So we can look at the residual sum of squares, which is the variability or the stuff we can't explain, the errors left over when we fit the model that we fit. And we can look at the model variability, the model sum of squares, which is the difference, improvement, if you like, that results from fitting the model compared to not fitting it. So like I said, I like my cake analogy. So just to demonstrate it a bit more visually, the total sum of squares is like this big round cake. So this is all the variability and monkeyness that ideally we would like to be able to explain by adding predictors to the model. So we add a predictor to, or several predictors to the model, and then we work out how much that improves it, and we assess that using the model sum of squares, and that will give us a slice of cake. Now, hopefully a big slice of cake, because we want to be able to explain a lot of this, so we're hoping that our model sum of squares is a massive slice of pie. But there's still going to be some error left over, so that will be, hopefully a small slice of pie, and relatively speaking. Now, this model isn't strictly accurate, because this should literally dissect into like two halves, or not necessarily halves, but two sections, not three. But it's the only cake picture that I could find. So we're working out how much variability there is, and we're kind of slicing it up into 2 bits. And then we use these 2 bits in one of 2 ways. The first is we can work out what's known as an F ratio. And the F ratio is basically, we end up using, I'm going to come into this a bit more in a few weeks' time, but we end up using something called mean squares, which is like the average sum of squares, rather than the sum of squares themselves. But what they represent is the same thing. So don't worry too much about that. You can sort of conceptually think of them as sums of squares. So the F represents the improvement due to the model. So it's the model sum of squares, or mean squares, divided by the error in the model. So the F ratio is the ratio of how much the model's improved relative to how much error there still is left over. So obviously, if that ratio is big, if the F value is big, what it means is that we're explaining more variability. The model is improving our prediction a lot more than it has error in it, if you see what I mean. So it's kind of it's almost the ratio of how good the model is compared to how bad it is. So if that ratio is big, if the F value is big, it means the model's a lot better than it is bad. So it's more good than bad. The other thing we can do is to use something called Rsquare, and this is just it's the ratio of the improvement due to the model, so the model sum of squares, relative to how much variability there was to begin with. So it's literally the proportion of variability that is explained by fitting the model. So SPSS computes this, using these sums of squares. It also, if you look at the values of the outcome that you would get from using the model, so the predicted values, that's what they're known as. This R-square is actually it's kind of related to the correlation between the values you actually observe and the values that the model predicts. So it's literally the Pearson correlation between those two things squared. The other thing worth mentioning, so the R-square is useful because it tells you proportionately how much variance is explained. So you can come up with a sort of, we fitted our model, it explains 30% of the variance or 10% of the variance, which is quite a useful measure in a way. The other thing to be aware of is SPSS throws out an adjusted version of this, which you'll see in the output when you do your practical class. And what this does is to estimate the value of R-square in the population. So the R-square that you normally look at is based on your sample data, but the adjusted R-square is an estimate of what R-square will be in the population. So it tends to be smaller. So it sometimes gets referred to as a measure of shrinkage. So it's a measure of how much, basically how representative the R-square you have in your sample is of the population. If the values, the R-square and the adjusted R-square are very similar, then it means that your R-square is a sort of a good approximation of what's going on in the population. So your sample is therefore presumably a good approximation. If the adjusted R-square is a lot smaller, then what it means is your sample data is quite different from what you're likely to get if you'd been able to test the whole population. So they're kind of the key concepts to take into your practical class. First is the idea that we can fit linear models. We can extend them to add multiple predictors. Each time we do, we have to estimate a beta. The betas tell us about the shape of the model, the size and the direction, the relationship between the predictor and the outcome. We can significance test them, so we can test whether they're different from 0. We can construct confidence intervals around them. For those significance tests and confidence intervals to be accurate, we need to assume that the sampling distribution of them is normal, and we can use bootstrapping if we're in doubt about that to give us pretty accurate estimates. And finally, we assess the model, generally, how well it fits the data, using either an F-test, which is sometimes known as ANOVA, or this R-square statistic. So all of this is going to you're going to do some examples in your practical class, and come up against these concepts again, and hopefully that will kind of drill them in a bit more. And then next week we're going to look at working out whether the model we have is kind of biased or not biased, and a good representation of the population.